Well, thank you very much, and to the organizers of the entire program and also of this workshop to give me the chance to tell you about some of the work we've been doing over the last more than a decade by now. And I'm going to also use the opportunity to be the second speaker of the workshop to give you a little bit of an introduction to implicit solvation models, to kind of sort of address some of the questions several of you had during the coffee break and which came up during the last question by Carsten. What are they good for? When should you use them? When you should not use them? And also to connect to some of the mathematics, because I think there's some important concepts we all should be aware of. So this work, I'm going to tell you, it was done by Eric Fonseca largely, especially the stuff about the active learning and going towards non-aqueous solvents. So VASPsol is one of those solvation models that are widely used. This is probably one of the most widely used one, VASPsol++, which Craig is going to talk right after me, is going to be the next generation of it. And if you, in other words, for those online watching on YouTube, don't use this one, use VASPsol++, because it's much more stable, has more features in it. But I'm going to talk about this one first, which is a subset of what VASPsol does. And because we've done something on the parameters for this model, which is going to be also transferable to VASPsol++ for non-aqueous solvent. Yeah, use Craig's version, which has a much more stable installation. The nonlinear terms, non-local models, and various other things we're trying to implement as part of the workshop are hopefully going to be available soon there. One of the concerns I'm going to address today is that the model parameterization for VASPsol was based on 9 small organic molecules in water. And when we would look through the literature, Eric actually is doing a lot of the GitHub responses when people have questions. Many people apply it to non-aqueous solvents. And then the question is, what do you do? Typically, the users just change the epsilon. Sometimes they change the dielectric permittivity. Sometimes they change other parameters. And we were very concerned, does it make any sense? And I'm going to convince you today that it doesn't make any sense, that the answers you actually get are pretty random. They're actually worse than random, I'll show you. And that there is a solution to fix that. And hopefully, people will use those new parameters and get slightly better results, and then also use better solvation models on top of it. So I'm going to, oh, that's the wrong button. Here was the original benchmark, 9 organic molecules. This was essentially based on what JDFTX method had implemented. We used the same molecules. We used essentially the same parameters for it. And it does a pretty decent job. All the energies in kcal per mole. It does a decent job for things solvated in water. I'm going to show you later that our validation shows that for water, the blue points, it's pretty good. For non-water, I'll tell you more. And then active learning is trying to put these points back on the parity line, that these actually can be improved for non-aqueous and aqueous solvents. And I'm going to tell you about some of the strategy we have, and also that you can, even with that method, improve solvents, which the model has never seen, which is kind of a fun little side note. Okay, so this work really started with Kieran Matthew. Kieran Matthew was the first grad student in my group to address solvation, and he implemented VASPsol. After graduation, he went into industry, and Chaitanya Kuluru took part of it over and implemented benchmarked the Poisson-Boltzmann solver and stuff like this. And about a year and a half ago, Eric Fonseca started looking at some of the details in the parameters for these non-aqueous solvents. Sean Flores was an undergraduate student in my group, and he was extremely helpful in collecting data, helping with the AI stuff. This work was supported, first of all, by IPAM, coming to those visits. This is not the first time I'm here. I'm part of the quantum theory project. We had a lot of discussions as part of that. And then the funding for Eric came from the Molecular Magnetic Quantum Material Centers. We're interested in interfaces in that case. Implicit solvation models helps there. Also, I need to point out that we're using a lot of CPUs and GPUs on our supercomputer Hypergator. There's going to be an announcement coming up soon about the new Hypergator, because we just switched from A100 to B200s, and it's really been in the top of the list of supercomputers again. We're having a lot of fun with that. Okay, I also feel like, being the second talk of the workshop, that I might be the right place to give you a little bit of a pedagogic introduction to what solvation models are, and try to connect to some of the mathematical concepts, and I think some of the underlying principles, because I personally, just coming back from my thermodynamics class, really believe that if you do the underlying thermodynamics correctly, you start with the right expression, derive everything self-consistently, it can help us really better understand what terms should we turn on in solvation, Where do they come from? Do we have the right formalism that we're not contradicting ourselves? So I think, Carsten, you probably already said a couple of things about solvation models. That might be.
I refer to you.
Thank you. Oh, thank you very much. And so the basic picture is, if we want to model any fluid interacting with a surface, we really need to understand thermodynamically all the statistical mechanics. What are all the configurations there are? That's an incredibly large number. There's going to be fluctuations of everything in there, etc. And sampling that efficiently from a DFT point is probably insanity. From a machine learning potential and a classical potential stuff might be doable, but do they have the right accuracy, etc. And so implicit solvation model try to make a very fast shortcut through that by just replacing all the complications with just some thermodynamic averaged equations that describe the response of the fluid to something happening near the surface without having to go through all the technical issues of sampling, the quantum mechanics, etc. Of course, as a consequence of that, it's a drastic approximation. And like Carsten pointed out in the previous talk, making sure that what you approximate is a small quantity to begin with, that your approximation is not going to affect what you do at the surface is important. Another important distinguishing fact, and I feel like we need to say here too, is that these models are not intended to describe kinetics. There's no kinetics in here. These are thermodynamic averages. We describe thermodynamic averaged fluid in front of an interface and try to do that accurate as possible. If you now look at reactions happening in there, you don't have any kinetics in your fluid, and you need to be aware of that. That's why putting a layer of explicit molecules at the surface to capture that kinetics effect and have the rest just be thermodynamically averaged might be a suitable approach, as Carsten pointed out. Okay, efficiency, thermodynamic averages, that's what we're going to look for. So we try to get rid of the sampling. And so the goal is really to replace all, oops, that's the wrong button. I knew that's going to happen. All our explicit molecules. Here's a picture of Schenker, who unfortunately couldn't come to this workshop, by something which looks like a smeared out density distribution or charge distribution of what the solvent does, and gives us the right thermodynamics for the system of interest. So we're replacing explicit solvent molecules with a dielectric continuum. And there are many models available. VASPsol wasn't even the first one. Fatterberg and Gigi did things before, many people before them. And JDFTX came out before us, which is a version which couples it to classical molecular dynamics instead of just implicit equations. We have Salza and Candle are solvation models on top of it, and Craig is going to tell you all the glory about how he really built a very quantitatively accurate model out of what we had in VASPsol. The basic idea underneath it is that we got to do a spatial decomposition. We have parts we want to describe quantum mechanically. This is going to be our electrode, especially our electrode surface. We need to have the electrons in here. We need to have some reactant on the surface explicitly described quantum mechanically. That's not illustrated in that nice picture here. And then we got our double layer here, our ions in solution, and then our liquid further out. And we're going to describe all this using essentially electrostatic and implicit solvation model. So the electrolyte region is going to be implicitly described by a Poisson-Boltzmann equation. In the interface region, you may have some explicit molecules that react, maybe a couple of bystanding molecules that make sure that the kinetics isn't wrong. And your solute region is explicitly described by TFT always. So I want to, at this point, come to some of the mathematical background and the fundamental physics background. I want to make sure that when we describe implicit solvation model, that we do realize where they come from. And they have to come from an energy functional perspective. We have to come up with an energy expression, including all the fields that are relevant, which are the charge density of the electrons, the external potentials from our ions in the solvent, that's all the DFT side of things. And then we have to describe in our solvent what are the relevant thermodynamic quantities, which is the distribution of charges, ionic charges, the water density, etc., and etc. in the liquid. And we're going to describe our implicit solvation model by that combination, our quantum mechanical solute, our interface region, and our continuum solvent. And we need to write out in type of energy functional. In this case, what's typically done is writing a grand free energy functional. I'm going to call that omega. It's often called also F, or it's going to be called A in some of the talks. So you're going to see, I think Craig has some different symbols for that. But what it is essentially taking the internal energy of a system and subtracting a rho charge density times potential term of it from that to get to a grand canonical type description for the charges. And this, we have to use the variational principle to minimize that with respect to whatever fields we have to actually get the Euler-Lagrange equations that we're then solving in our implicit solvation models. I'm going to have two fields in my model. You can have more, but one is going to be the explicit charge density of the electrons. That's going to be largely described by DFT, but it matters for the electrostatics. And then we're going to have the electrostatic potential phi. And I'm also going to say what happens if we put in ion concentrations there as well in that description. Euler-Lagrange equation, we vary that, and the variation is 0. And so we need to now figure out, when we describe implicit solvation models, what are the contributions to that omega? What are the energies that matter in the system? So we're going to describe parts by D of DFT, and we're going to describe parts by the solvent, and all the magic happens in that omega solvent. What are the terms we turn on, use, and describe? We have an electrostatic term in there. I'm going to say more on the next two slides about that. And then you can add any term you like. So if you have an energy expression for some other contributions, keep adding them. There's parameters in them. You have to optimize them. And with some luck, it might improve your description. You have to have some cavitation energy. How much energy does it cost in a solvent to make a cavity where you can put your solute? There's some dispersion interaction you can add in there. How is the interaction across that interface driven by dispersion, van der Waals-like interaction? You can put in repulsive terms, for example, between the solvent and the solute itself, or also between ions in solution. What are the finite volume effects? And you have to, if you want to really do an electrolyte, not just a dielectric, you have to include the ions in there as well. So here's some of this, what I just essentially motivated. So for the electrostatics, what we typically put in there is just our solvent polarization. For the ions, we're going to put an ionic entropy. I say a little bit more about that on the next few slides. And the ionic shielding, that gives us our double layer formation. Cavitation, the solute-solvent boundary is described by that, van der Waals. And then repulsion are various types of short-range volume exclusions you can add in there. I'm not going to talk much about that. I think Craig might have a little bit more to say about the specific terms and what they lead to when you actually do your Euler-Lagrange variational calculus. So systematically including and adjusting these parameters actually does improve the fidelity and transferability. Some of the advanced model, which unfortunately Katie Schwartz, because of the shutdown, couldn't come, like Salsa and Candle do these things, but I'm happy during the next break or so to discuss any of those things with you. So how do we actually do that? So I'm not going to talk about the DFT side of things because I'm assuming that either you know it or you don't care. About the DFT side of things, I'm going to focus on the electrostatic side of things. And the electrostatics has an energy contribution. That's the internal energy of an electric field is proportional to the field strength squared, the factor half, and an epsilon in front of it. That's it. But we're not dealing here with a microcanonical or canonical ensemble. We're dealing with an ensemble where the variable we want to vary is actually the variable phi. We want the electrostatic potential, our controlling variable. So we need to do a Legendre transformation. We need to subtract from the internal energy the term rho s, my solute charge density here, or it could be the total charge density, times my potential, and then integrate it up over all space. If we do that, now we have an expression for that, and we can do our variational derivative. We can do our Euler-Lagrange equation, derive our Euler-Lagrange equation. We vary our potential by a small probe potential, eta or whatever we call it, and set that variation to 0. If you go through all the steps, and I'm not having them all on here because I think you've probably seen that in various introductory classes, you're going to get an equation. You do have to do an integration by parts on the first term, and you get an equation that the gradient or the divergence of the dielectric constant, its principal tensor, multiplying your electric field minus the charge density is 0, and that is nothing else but our Poisson equation with an inhomogeneous dielectric constant. So we're not pulling that operator through to get our Laplacian here, but that's it. This is the equation we're going to actually solve today for VASPsol, but I'm also on the next slide show you what happens and what's interesting when you actually have mobile ions in solution and maybe some other potential terms. How does the equation change? So that's going to be the Poisson-Boltzmann equation, and in that case, the assumption is, I just come back from the thermodynamics class. It's the simplest assumption we always make. What's the simplest assumption in thermodynamics? It's called ideal gas, right? Ideal solution model, ideal gas, all the same thing. So we just decided, I think whoever wrote this equation out first decided that we're going to just take the ideal gas entropy contribution, log of the concentration of the ions at position R divided by some reference concentration, and to our electrostatic term here. The other term is now, we do have now extra charges in them. These charges are the ions with concentration Ci. There should have been, as a function of R, times what their charges really are when you get the concentration times the potential. There's an electrostatic term from that. So you get an entropy, we get an electrostatic term. And then there's often added an extra potential term which could describe the repulsion between ions. That's useful for describing this term there. But this is the ideal gas contribution. So in other words, when you think about what the Poisson-Boltzmann does, which is used in a lot of continuum models, is very simple. This entropy term is way too simple, and maybe the first thing one should do is make these things slightly more complex and include finite volume and stuff like this, which has been done in the literature also. When you minimize this expression, for the first part, with respect to the field, you get this part is going to be the same as before. Here's that part of the expression. And for the second part here, you're going to get that the Stern-Leer part drops out because there's no phi associated with it. We simply get the concentration as a function of position times the actual charge. All that has to be 0. If you simply write it out in slightly different form, you're going to get your Poisson-Boltzmann equation out with now the charge of the electrons in your solute, and here is your ionic charges added on. This is a fully nonlinear Poisson-Boltzmann. You can do tricks like linearizing that to get a slightly simpler form, but this is what's implemented in VASPsol, in VASPsol++, and any of the other models we're going to discuss. But remember, again, it's ideal gas. We're really dealing with some actually surprisingly simple approximation, but it kind of works. There's a second variation we have to do because I jumped over that in the beginning. Sorry about that parenthesis being in the wrong place. It also depends on the concentration of all the ions. And interestingly enough, when you do that derivation based on that term, you get an equation you probably would have started with writing out. That equation is simply, when we minimize that, here it is, you get your entropy contribution kBT logs the concentration, plus now that repulsive potential and your electrostatic contribution of the ions has to be 0, one step, and you get what you probably would have expected. You get essentially your Boltzmann probability distribution for the ion concentration, the electrostatic term, and any kind of repulsive term you might want to add in there as well. In other words, the Poisson-Boltzmann is a result of that energy functional expression. This type of energy functional expression can be taken further. You can also take it all the way to classical molecular dynamics for the liquids. I'm not going to talk about that here at all, but that's another way of describing liquids in there as well. So after that introduction, I'm going to actually come back to just the Poisson equation. I'm going to skip Boltzmann for today because I want to answer a few questions about parameterizing solvation models to experimental or computational data. How can we do that effectively? And so I'm going to show you that for VASPsol, a model which has a very small number of parameters, there's 3 relevant parameters. I'm going to show you what those are, how we optimize them using experimental data from 2 types of databases. But what are we going to do? We're going to first ask, how accurate is VASPsol, the 2014 parameters which are in there actually, when you look at an extensive data set? And then I'm going to try to answer the question, how do you improve the predictive performance using a data-driven approach, using a significant number of solvation energies and some machine learning models in order to really speed up the optimization. So VASPsol, Kieran, here he is, and we had several authors from the Arias group, which helped with some of the development, was published in 2013. I think the paper, I'm calling them 2014 parameters. I don't know why. Here we are with that original model. That's just dielectric screening. The second model, Kieran had graduated, Chaitanya had taken over, that was finished quite a few years later. That included the electrolyte model. The way we describe in the paper, we mostly talk about the linear one, but there is a nonlinear version in there. The stability is dramatically improved by VASPsol++, so please use that one. It's widely used, so we really think we owe the community a good estimate. How accurate is it actually, and what do you do when you put something other than water in there? So the basic idea is that we're starting with the linear approximation that the polarization is proportional to the electric field. We do have a version where we have a nonlinear version for that, where we include that at high fields, the rotational degrees of freedom are saturated and you just have the electronic polarization. But again, for many applications, the nonlinear part actually doesn't matter that much unless you have very high fields at your surface. And it's actually not the electrostatic potential which controls that. It's really the field you have between cations and anions if you have an ionic surface, like in lithium fluoride, beryllium oxide, and some of those kind of very ionic materials. So we have our, oops, I'm pressing the wrong button. I want to say a few things here. So we have our DFT kinetic and exchange correlation. Our electrostatics is here. And here is the energy of the field I had mentioned. And here, in this case, we introduce also cavitation energy, which is just given by some estimate of the surface area times some interfacial energy, which captures the formation of the cavity and the van der Waals interaction with the surrounding in an approximate way. So now again, it's an energy functional expression. You got to do your variation, and you're going to get extra terms for your density functional calculation, which you need to include in your calculation. There's a couple terms, and that's all implemented in VASP self-consistently, in VASPsol and VASPsol++, following that principle. And you modify your Poisson solver, which in DFT is normally just simply dividing by G squared in plane wave DFT. Here you have to do something a little more complicated because your dielectric constant is now a function of position. So in other words, this model needs to know where does the dielectric constant turn actually on. And the dielectric constant turn on, and that was first introduced by Fatteberg and Gigi as a function of the local electron density. Where your density becomes smaller of your solute, that's where the water can approach, and that's where the water density should become large. Here's a small molecule where we show a cut through the molecule from the center to the outside, and when the electron density, the red curve, becomes small, at that point your dielectric constant should increase. Chemists in the 80s in their solvation models and 90s have actually used a hard sphere approximation, saying we're just using van der Waals radii and stuff like this, and at the surface of those, we're going to go from an epsilon R of 1 to 78. That's not a good idea if you have a plane wave basis code. We really do not like hard surfaces. The numerics just doesn't make any sense. So we have a function, it's a complementary area function of the log of the electron density, and there's two parameters in here which are two important parameters for our solvation model. What is the critical density when that happens? So when n over that n0 becomes 1, that's really when that changeover from solute to solvent happens. And then we have to define the width of that interfacial region. This is just that parameter sigma. So these are two parameters we have in the model. The other parameter we had was that interfacial energy tau, so 3 constants. Very, very simple. I want to point out that when you actually do some electrochemical calculations with the original VASPsol model, and I think many of those hold also true to some extent for some of the other models, these parameters NC and sigma change various properties. NC changes, of course, how large your cavity is and how close the solvent molecules approach that. So when you make NC smaller, you increase the size of the cavity. So this is something that might be relevant for some application when you find that the water seems to approach regions where it really shouldn't be. And the transition width is an important parameter because if you make the transition width too sharp or too narrow, there are different effects that happen. If you make it too broad, you get some unphysical oscillations in your system. If you make it too narrow, you don't have enough grid points in your plane wave basis to actually resolve it, and that leads to additional noise in some of the other terms. So you really ought to be careful in not changing it too much from the default parameters unless you know what you're doing and have really high cutoff energies and stuff like this. So these were the default parameters for VASPsol. Right? So they were essentially the same taken as the JDFTX paper at that same time. And that was the original benchmark. I would consider that perfectly acceptable energies. And so the question is, how does that carry over to a larger data set of systems? A larger benchmark would really find us the limitations of those parameters. And so we want to optimize those parameters to increase the final DFT calculation. And I'm going to give you now first an overview of what I'm going to talk about next. We're going to start with these initial parameters, and we're going to try to optimize those parameters to come up with better parameters for water and for other solvents. And we're going to do that using two data sets. One is the data set by Don Trula at the University of Minnesota, and the other one is a data set solved at TUM from the Technical University in Munich. And we're first going to apply that to the default VASP parameters and figure out what the test errors are for the MNSol database. And then the second part of our analysis, we're going to train on the MNSol database, and we'll also do the validation of that. And in the testing data, I'm going to show you independent data from the solve at TUM data set. I'm going to show you that conventional optimization is simply just trying to vary the parameters, finding a better model, and then applying it to the entire set fails. It's an overfitting. And then an active learning approach can overcome that, and then show you how well does it really do the final model. So the MNSol data set by Don Trula is experimental solvation energies. It's available online, and it contains 274 aqueous solutions and 679 non-aqueous solutions. There are 19 unique solvents in total in there, so water plus 18 others, and there are 392 neutral solutes. We're only looking at neutral solutes in that work right now, because charged ones is a little bit of a different story. We haven't gotten to that yet. Traditionally, we recommended people, if you use VASPsol for anything other than water, just change epsilon. It might work, right? Okay, we didn't know better. Nobody had tested it. And what happens when we do that? We're changing epsilon for all the 19 solvents, run the calculation, and this is what we got. Blue is water. Water is always blue, right? So it looks actually pretty decent, right? It has an R squared of 0.88, and the mean absolute errors, they're larger than what we had for the 9 molecules we had, but they're certainly not something where you say this is useless. This is a useful set of values, I think, for water. For non-water, well, yeah, now you got to really kind of hold your breath a little bit for a second. R squared is minus 0.437. And I'm teaching in an AI class, and the first thing we also always do when we do those parity plots, what's the range of R squared that makes sense? This goes from 1 to 0. What does it mean when R squared gets negative? That's mathematically perfectly plausible. It means that randomly guessing, just picking the average, for example, of your distribution, would have given you 0. You would have been done. Pick the average, be done. This does worse than picking the average. This is actually effort, right? You have to put in to get something worse than just picking the average. So this is terrible. The errors, 5 kilocalories per mole for the MAE, 30 kilocalories for the MSE. I mean, look at that blob. It's in the wrong place. It does everything wrong. So that was the motivation. When Eric showed me that, I said, yeah, we got to do something. We can't let people run VASPsol, or I guess VASPsol++, because you also don't have parameters for other than water, right? With this kind of information. We got to fix that. So very motivational, but very terrible. So fine for water. Don't just change epsilon for anything else. You got to do at least a little bit more. So that's the first data set, the MNSol. We actually ran all the calculations, all the optimization with that data set. And then we figured out, once we were done, we said, wait a second. We made a very fundamental mistake for machine learning. We didn't do an 80-20 split for our training validation data and 20 for independent testing. We didn't have an independent testing data set anymore. And then we said, well, there might be other data out there. And we found that data set from TU Munich, which contains 67 non-aqueous solvents, so actually way more solvents than we're training on. I'm going to show you a lot of consequence of that. And 5,952 solvation energies. These were obtained from partition coefficients. There's a little bit of overlap between those two data sets. And we checked that the solvation energies from that database and from the MNSol actually are consistent. We do a parity plot over that subset of a few hundred mixtures that are identical. We get the same solvation energies, very, very accurate, way more accurate than our VASPsol does anyway in the end. So these are consistent. And when we look at that data set, and now we're just going to use the default parameter of VASP, we essentially find the same thing we've seen before. These are now, this is 1,800 solutions we calculated, and we see, the R squared is again terrible, and the ME and MSE are also just not particularly useful. Here I'm going to say there's 48 solvents we looked at and 351 solutes in this case, and there's 29 solvents that are not in MNSol in this one, and I'll say a few things later about how we can learn on one database and then extrapolate to solvents we've never seen. So VASP performs poorly on those non-aqueous solutions, as we already know. So this is where we start from, and the message is, if you use VASPsol or VASPsol++, do not just update the epsilon and use the other default parameters for anything other than water. Water works, everything else, you got to do a little better. I want to compare to some other solvation models just to kind of sort of set the stage where we are compared to other kind of ideas. And we're falling right smack in the middle here compared to some of these other models. So it's a good model for water. For not water, as I said, we got to improve that. So now how do we do that?
Sure. I don't know if you're going to address it, but if you go back 2 slides, can you just tell us, so what is the main reason for the systematic shift?
For that systematic shift? I think I do have an answer to that. I come a little bit to that. That is for most of these other solvents, they have a much smaller dielectric constant. So I think the turning on of the epsilon really needs to be described differently. In those cases, we go into a smaller dielectric constant. Also all the other things have larger molecules. The width of the transition region has to be different. Those are the main motivations for why for those other solvents we're just doing things wrong, right? It is we think those 3 parameters. Well, I'll show you that we're doing much better when we train on those solvents. And so we're getting quite reasonable accuracy, and it's exactly with this, the width and where these things turn on. Just water is special. It's the tiniest solvent molecule I guess there is, right? Are there solvents which are smaller than water? Okay, well, we don't do CO. Good, but see, there's one. But all the other ones in the database we're looking at here, right? We're not looking at supercritical CO. No, I don't know, CO2 is different from CO because I don't even know CO. Thank you. It's just bigger molecules. The width is wrong. The cutoff, the start is wrong. That's mostly what it is. And the epsilon is usually quite a bit smaller. Okay. So we're going to start out, I'll show you that conventional optimization is not going to work. I'm going to then show you an active learning loop. And I'm going to show you what in the world do I mean by these little plots. What are the features we actually try to do that learning loop. So we started out doing a grid search to identify an error surface for the width and the cutoff. We actually didn't want to do that for all the 600 or whatever your solvent mixtures it is. So we did some down selection to a smaller number of solutes that were representative. And we're using something, the Cosmo Sigma profile, to do all that. And let me say something about the Cosmo model. The Cosmo RS model is a dielectric, an implicit solvation model that describes some electrostatics, hydrogen bonding, van der Waals interaction to estimate various solvation-related parameters: activity coefficient, solubility, partition coefficient, phase equilibrium. It's a company that does that. And so if they've done a very nice job of parameterizing all those parameters, and they get very accurate models, I showed you on the earlier slides that they can do quite well. The basic idea, and this is what we're using from that model, we're not using most of the rest, is that if you got a molecule like water in here, they define a surface, they divide the surface into segments, and they calculate for each surface segment the charge density on that surface. They'll make that a histogram. That histogram is called a sigma profile. It's a nice electrostatic type of fingerprint which tells you what does a solvent molecule and a solute molecule, for example, look like. What is the charge density? How might they interact? So we think there's a fair bit of physics baked in, how much of a dipole you might have across that thing, how large is the charge distribution from the max to min, etc., these kind of things. And we think machine learning, giving that information, might actually have a shot to figure out which solvents are similar, which solutes are similar, and we can put them into groups. So here's a couple illustrations for what these things look like, right? For benzene, for example, you see a single peak at 0 here. For some of the other ones, you're going to see some very polar examples just to get an idea. So we think the Cosmo Sigma profiles feature as our molecules in a good way to interpolate across different mixtures and to give us an idea of what the electrostatics might look like. So we did that on all the molecules in the data set, and then we identified 9 solute molecules, which come out when we do a principal component analysis to get from 51 dimensions, when we look at these profiles, to 2 dimensions. We see that's indeed clusters, molecules. Some molecules have a similar electrostatic on their surface, and we select 1 molecule from each cluster. Here they are. And there are some very non-polar, some which are much stronger polar molecules. And when we plot the sigma profiles of those 9 and show them against all of them, and also show the sum of them, we see they actually represent the overall distribution quite well. So they're probably better than just randomly picking some with outside information about the surface. Then we actually did the calculation. We used a 4x4x4 grid on those 9 solute molecules in water. That's 576 calculations, so a moderate number. Here's a zoomed-in region of what the surface looks like in the central region. And here's our original VASPsol parameter. And when we optimize it on that surface, this is the optimal value is actually right here. The colors are a little different. I'm not exactly sure what happens there. But that's the best one we're going to find when we optimize that. Here are the changed parameters. They're obviously not very largely changed. And we find that indeed now our VASPsol error was 1.2 kilocal. We go to 1 kilocal. So it's a modest improvement. However, if we now do the calculation on all the molecules we have in the system, we validate on the remaining 265 solutes, we find that the error actually goes up. So it's overfitting. It doesn't actually help. So direct optimization, short of doing it on all of them, isn't really a very viable approach. And remember, this is just water. In the end, we want to do those calculations on the non-aqueous solvents as well. And that's just not a very efficient approach. So grid search produced parameters that overfit, and doing it more extensively, we didn't want to do. So we did something else. We did a Nelda-Mead optimization where we start with the values we had previously and then let it wander around as the gradient-free optimization and see if it can find some better values. These parameters also slightly shifted, similar plot here. And if you look there, we go from 1.2 to 0.4 kilocals per mole. And then we go to validation error again. We overfit. So we clearly picked too few solutes from our principal components of our 9 clusters. If you would have done more, that could have worked. But it's not a very good approach. It also tells us, wiggling around in that space a little bit, we're not going to get much improved parameters. So we might as well do something different. And the main message, I feel, is like water parameters for the default are actually pretty good already. And trying to optimize those for more systems doesn't really help much. So that brings me to the second part, which also is going to include now the other solvents, which I think is the most exciting part, is that we want to do actually, instead of doing that overfitting, we want to really do a much better approach, go into more solvents where we can do even less of those calculations, and we need some sort of active learning approach. So brute force is not a good solution. What we're going to do is we're going to develop a neural network surrogate models. And what the goal is to try to limit the number of VASPsol calculations that are required, and then make sure that that can generalize to solvents, which we don't even have in the training set. Can we actually do that? The answer to that is partially yes. To the second question, we can even improve for unknown solvents how it works. So we use those sigma profiles to describe our molecules. So we start with our structure for solutes and solvents, and we do our DFT Gaussian calculation, which just gives us a sigma profile. It's just a charge distribution on that surface. We also, since we have the sigma profiles, we run it through the Cosmo model and get an infinite dilution activity coefficient, which we're going to just use later on as an additional parameter for our machine learning. I've already mentioned that we use those sigma profiles to kind of sort of see which molecules are similar, which ones you have to look at. We did that PCA on the 2D sigma profiles and selected a solute from each cluster. Now you have a set of selected solutes, a select of parameters. We did the DFT calculation, get our solvation energy with DFT, can compare that to the experiment, and get what I call E is the error in the solvation model. How large is the error between the DFT and the actual experimental solvation energy? Here's the equation for that. This is the thing we're actually going to train. We're not trying to learn solvation energies. We just try to learn errors on the solvation energy. And then we're going to optimize and minimize that error using the parameters. And so those are the ingredients for our active learning model. So how does that actually look like? So we take those sigma profiles to featureize the mixture. For every mixture we're going to try to learn on, we take the sigma profile of the solute, the sigma profile of the solvent, we'll simply concatenate that. In addition to that, we have a couple other parameters. We have our model parameters, which go in there. Those are the ones we're going to optimize in the end. But in our model right now, we're going to predict the error of the calculated solvation energy based on the system we use, based on the 3 VASPsol parameters, the dielectric constant of our solvent, and that infinite dilution activity coefficient from the Cosmo Sachs model. Those are scalar features we're going to add to those in our network. The final model will give us the error depending on that, and then we're going to minimize the error over all the molecules in our training set, even the ones we don't have any data from. And that's the advantage of doing machine learning here. Yeah, and I think the idea here is these surface charges help transfer interpretability of the model across different kind of molecules. Good, I think that's perfect. So we have, we start with, we had in the Nelda meet and in the direct grid search, we had about a little over 11,000 VASPsol calculations done already. So we start with that. That's our very first step for doing our active learning on that. We're going to get, we have the sigma profiles for everything, our VASPsol parameters, which we chose here, and the infinite distribution constant. And we're going to do our custom neural network run to predict these errors. Next step, after we have that model, I'm going to say a little more about what that model looks like. But after we have the model, we're going to minimize that error over these three parameters. We're going to find the minimum. We're going to find a new set of parameters. For the new set of parameters, we're going to calculate the solvation energy for 953 mixtures for that new set of parameters. We're using DFT. We get new errors for the solvation energy. We feed those new errors back into our training data for the neural network, and we're going to go through that loop 3 times. But after 3 times, the parameters end up not changing significantly anymore. So we get an improved model every single time, feed it back. So what does the model look like? So we had those sigma profiles, and we had those independent features down here. And so we use a convolutional neural network. We end up with convolutional kernels and pooling that we're going to get to 10 channels in between. You go first to 5 and then to 10 channels. That was our hyperparameter optimization. And the kernel size is 1 by 3. And we got a large feature. We add these independent features, and then we have a small feed-forward multi-layer perceptron at the end to get us our solvation energies. And so when we do our test training and validation, this model turns out to be reasonably well. So we get a pretty good predicted versus true based on that model. Now we have a model that we can use for minimizing the error of our solvation model over these parameters. So we're going to now take that surrogate model and just with that surrogate model minimize the error by varying NC, sigma, and tau. So yeah, so essentially what we're doing is a form of delta learning, and it allows us in the end to even look at mixtures where we don't have experimental data, because as long as we have this input, this will give us the error our model would give, even for data it has never seen. So this is another way of representing that. We're going to have our model here, which is just based out of the experimental data minus the calculated data. If it's small, we're going to just, if the mean error is actually small, we're done. But if the mean error is larger than that, we're going to optimize over our surrogate model. We're using a particle swarm method. You could have used other methods. Particle swarm is pretty efficient. And then we get new parameters, feed it back in, we loop 3 times, and we get our optimal parameters. So what do we get? So here are the default VASPsol parameters. This is summarizing all the different ways we've done things. Sigma and tau, our error. This was the grid search we've done previously in the Nelda meet, and both of them overfits, the mean absolute error goes up. This is for water now, right? And so here's for our particle swarm surrogate model, VASPsol active learning loop. The parameters do change, and our error actually does improve. But again, it's pretty marginal. So in other words, for water, we're not gaining much, right? Water is really not the system where we had a major problem. And so so water, if you can look at it here, is the blue points. It goes from this to this, and this is essentially only a marginal improvement here. So I don't think you would worry about that too much. Actually, the R squared goes up, but the ME and MSE goes down. So interesting observation. Where it really made a difference, that whole approach, is for the non-water system, the non-aqueous solvents. This is what we had to begin with, that blob off the line. So it's like R squared being minus 4.37. So if you look at it now, you get an R squared of 0. That means taking the average would have still been a good way. But if you look at the data, it actually doesn't do too bad. It does predict the trends much better. The curve is in the right regime. and get an MAE of 1.36 and a mean squared error of 3.25. So we really have a much better shot of describing non-aqueous solvents after going through that system of, and so there's some systematic errors. We've actually looked at some of these, and we're trying to figure out why some of them actually fall on a line which looks a little off here. And it may well be that the VASPsol model just doesn't have enough parameters to describe that well. So the overall MAE is now 1.3 kilocalorie per mole for everything. And at this point, we ended up having to do 14,000 solvation energy evaluations in VASP. So a reasonable number. So far lower error before, but clearly there's further improvement needed. So applying this approach to models which have more flexibility, like maybe VASPsol plus or the SALSA model, might really help improving the description. So how does it do when we now compare? To come back to Graham's question originally, why are those models so bad? And so here's a plot where we looked at different solvents as a function of dielectric constant, going from benzene all the way to water. Water, we don't change much. And what you systematically see, if you go to smaller epsilon, and all these molecules are also larger, you'll see that the model actually does quite a bit. The original model does pretty bad. The new model, they all do about the same as water now. So in other words, really making sure that that cavity forms, what's a critical charge density, what's your width of the distribution, needs to be appropriately chosen for the right kind of molecule. Water is essentially an outlier when it comes to solvent. It's very small and a very high dielectric constant. The other ones need different parameters just for forming that cavity. That's one of the take-home messages. So all 19 solvents have improved validation MAEs, and so the default parameters, the errors are much less the higher the dielectric constant also is still. So but as I told you, we hadn't actually left out a completely independent data set in that work. So we needed a data set which had new solvents never seen. And so the solver TUM was ideal for that because not only did it have mixtures we didn't include in our original test, even more important, it had solvents in that the model has never seen. And since the Cosmos Sigma profiles idea was that this is actually describing something electrostatic, how does it actually convert? 2 minutes? This is one of the last slides. So if you look at it now, this is now a data set that's independent. And so we're looking at overlapping and non-overlapping solvent between the TUM data set and the MN-Sol. The data sets, so this is the original parameters, and it's just terrible, right? You don't really want to talk about that. Here's what happens after optimization. If it has seen the solvents, but not necessarily the solutes, so the mixtures went in there, but at least the solvent had learned something about, well, the green points, I think that's something which is an improvement. Is it good? Well, the R squared is 0.6. The MAE is actually pretty reasonable here, right? So the density of points right on the line is good. So overlapping solvent, but not seeing the solute-solvent mixture, actually does work. So that's a good result. For solvents it has never seen, it certainly improves. It goes from an R squared which is ridiculous to an R squared which is very bad. So I consider that an improvement. Is it useful? No. I think you want to make sure that if you want to use the VASPsol or VASPsol++ for solvents and you've never done anything to improve the parameters, you're probably in trouble. So you probably want to look at refitting a model like ours, or at least tuning it to some systems for solvents which we didn't train on for doing that. We might actually just throw all the data in the active learning loop and do a couple rounds for that and give parameters, but then we don't have independent testing data, right? So then you just get a validation error. Good enough. We haven't done that yet. This work isn't quite complete. Yeah, so since I'm low on time, so interesting enough, the model certainly generalizes to unseen mixtures of solvent and solutes, but if you have never seen any solvent like it, it improves, but there's lots of space to improve further, in addition to having models which have more parameters. Let me skip that. This slide is essentially the same slide as we have before, except for all the solvents, so that we can see for the ones which are in the training set. So it's a little bit too much to see, but we see essentially the same improvement I described on the previous slide, that you do need to have some overlap in training and testing data to get some reasonable results. I'll skip the analysis of how the sigmas change and just come to the final slide. That first of all, solvent models describe thermodynamics, not reaction. That was one of my take-home messages, that is by construction, and when you look at VASPsol, VASPsol++, and other similar models and try to expand them to solvents you've never seen, you better have some information on how to change your parameters. Don't just change 1 or 2 parameters and be done with it. You really want to change all 3 parameters in VASPsol or more in the other systems. And active learning can minimize the number of required DFT calculation you need to do in order to really get to a model that transfers using features which describe the charge density distribution on the surface, like Cosmo. Those sigma profiles can help you, give you some generalizability across these different systems. Well, thank you very much for your attention.